Okay, thank you very much. Good afternoon, everybody. I think it can be argued that one of the most notable scientific achievements of the past 50 to 60 years has been the dramatic improvements in weather forecasting. And one major contributor to this has been space technology, and supported by, of course, the exponential advances in computing power and computer models. What I'm going to be doing is showing some examples of satellite products, in particular satellite imagery, and how we use that in a day-to-day fashion in weather forecasting. So basically, I'll be showing you lots of satellite pictures. So it's worth saying that the volume and quality of satellite pictures has moved on remarkably in the time since the very first satellite pictures were received from Tyros in 1960 to the sort of products we typically get all the time now and take for granted, which have resolutions of a kilometre or less. So I'll be showing satellite imagery from a variety of satellite channels, but just as a taster, here's a typical example of the sort of thing we can get available now. This is essentially a visible high-resolution satellite picture. The British Isles there, Greenland there, taken a few days ago, just to the northwest of the British Isles. You can see pinpointed some beautifully defined circulations there. Denmark Strait, one northwest of the UK. We can see some very clumpy looking shower clouds and cold air coming towards the UK. And there's Iceland, beautifully picked out by the snow cover. So in a way that, I think, sets the scene. And I'll also be, as well as showing some standard products, I'll be showing some slightly less familiar satellite products. But to, again, set the scene here, this is a visible satellite picture taken from Meteosat satellite, geostationary, sitting 35,000 kilometers above the Greenwich Meridian. And this basically just is a black and white version of what you would see if you were sitting on the spacecraft looking down, with, of course, the coastlines and lat-long lines added. A wealth of features you can see here. That broad band of cloud there is essentially a cold front, very bright, thick cloud there. And behind the cold front, we've got very cold air streaming down from the Davis Strait over warmer and warmer, relatively warm ocean, and it bubbles up in that sort of convective, lumpy texture. And, well, over Europe, a ridge of high pressure there giving some marvellously clear skies. What else can we see? Well, over Africa there's a system. Those coloured crosses I've put on the map there are lightning reports. And so we've got an area of thunderstorms over Tunisia there. So straight away you can see there's a wealth of different products, different features we can see. Now, visible satellite pictures, great, but we need daylight for those, and in the winter there isn't much of that around. So what we can do is to look at infrared pictures. Now, infrared pictures, when they first came in the late 60s and early 70s, meant that we could have 24-hour satellite pictures. What these show is essentially the temperature of the cloud or the surrounding surfaces, and it's color-coded or grayscale such that white is cold cloud tops that are very high in the troposphere, maybe 30,000 feet, and successively darker and darker colors are warmer cloud tops or warm land surface, like the heated African landmass and Iberia there. So it basically gives us some information in 3 dimensions, if you like. So this is the same cold front here in the IR with an ascending mass of air, lower, warmer tops down here, getting colder and colder, and the development of a circulation here, which was to become Storm Gareth, that you may or may not remember hit us on midweek, giving very strong winds across the whole country, including this area. And what else can we see? We can see this greyish cloud here is all a much lower, warmer top cloud, very bright in the visible imagery, but it shows it's much lower down in the atmosphere. And the system over North Africa there, extensive cold tops associated with the thunderstorms. So again, a nice variety of features that it can show up. And we use these satellite pictures as a basis for our standard meteorological analysis that I'm sure a lot of you have seen. That ribbon of cloud there associated with that, what is a vigorous cold front. The isobars in yellow, these are derived from a combination of a previous model forecast and surface observations over land and sea assimilated into it. And you can see the developing low pressure centre, the developing storm there approaching Iceland at that stage. We use analysis in satellite imagery in meteorological analysis. And here's another product we sometimes use. So instead of the infrared, which is the 11 micron channel, window channel, we're looking at emission from water vapour here in the 6 micron channel. And what this shows us is the total amount of moisture in the atmosphere. It's focused around about 24,000 feet in the atmosphere. So it's very useful for diagnosing what's going on in the upper air. And essentially what that's showing is a large trough down there. Front shows nicely. And notice there's very sharp edges here between the black, which is a very dry air, and the greyer and whiter colours, which are moist air. Those sharp edges are very often associated with jet streams, for example. So I just highlighted on there the position of the jet streams, which are the very fast moving currents of air at around about 30,000 feet, which aircraft try to use to get tailwinds or avoid for headwinds. So straight away, a satellite picture like that, you can get an idea from the edges of the moisture, confirm the position of the jet stream. So in fact, you can confirm the model's position of a jet stream by comparing it with satellite images. And there, for example, we can see a subtropical jet stream coming up over Africa there. So basically, 3 forms of imagery there that can give us both an idea of large-scale motions as well as much more detailed, smaller-scale features. Now, that cold frontal zone, a day later, moved into the British Isles, and we can blend satellite imagery with imagery from the UK weather radar network, so you can see which are the active rain-bearing parts of the cloud. And that was a system that went over us last Tuesday and gave us a very wet day in this area. And that swirl there is Storm Gareth girding its loins. Now, if we zoom in on the map over southern Britain, we can see the different colours represent different rainfall intensities from the surface radar network. And that rather slightly contorted rope-like structure there, with a very heavy narrow band of very heavy rain, is the actual cold front itself, just about to come down across Exeter and introduce an instantaneous 5-degree drop in temperature. So satellite imagery blended with radar imagery, you can get a tremendous amount of local detail in terms of what is going on. And that picture shows over the same area the fact that there were 9 or 10 degrees ahead of this front, 5 or 7 degrees behind it. So basically gives a picture of the sort of things we can broadly see. Now, one important application of satellite imagery is to monitor the formation of, for example, the formation of major windstorms associated with rapidly developing cyclonic systems. Now, this type of system, which I'm going to be talking about, the term weather bomb, has been coined particularly by the media because it's a sensational term that sells newspapers, basically. But it's a term that's used for a very rapidly developing cyclonic storm. And I'm just going to show, from an imagery perspective, how imagery helped us in the prediction of this particular feature. This event actually hit Scotland a few years back. And although this wasn't the same event, these storms can give rise to damage of the sort of thing you can see on those pictures that are quite serious. Here's an infrared picture, midnight, 3rd of January. This cloud mass here over and to the west of the British Isles is a developing cyclonic storm system, very vigorous depression. And it has a particular distinctive signature. There's the British Isles there. Notice this convex mass, this mass of cold cloud tops right, with this convex northern boundary. And secondly, notice this slot, this relatively cloud-free slot poking into the back of it, which is where the jet stream is entraining the system. And to the northwest of it, you can see this clumpy-looking cold cloud in the cold air, which is tucking into the back of the system. And that structure there corresponds to something we call in the trade a cloud head, and that is often accompanies or precedes by a few hours a rapidly developing storm which can give hurricane force winds. Now, if I just cycle through this at 6-hour intervals, 6 hours later you can see that the cloud head has curled round into this hook-shaped structure, which is, you can just see it there in the imagery, bearing down in towards Scotland. And in the next 6 hours, that's carved right across Scotland and formed into a very vigorous, into a circulation over the North Sea. And a little bit later still, there it is as a beautifully marked spiral, indicative of a vigorous cyclonic storm with very strong winds. I find it fascinating how you see these scales of structures reproduced from everything from a coffee cup up to a galaxy, these spiral motions. It's quite something quite fundamental. So what I want to do now is to home in on the stage where that particular storm was bearing it down on Scotland, and in that hook-shaped structure. Now, satellite imagery in these circumstances can show these tail-like structures emerging from the tip of the hook. It's in that area I've put the ellipse around. And these tails that are forming are often indicative of extremely fast, damaging gusts that form associated with a cyclonic storm. And they're caused by narrow tongues of air descending out of the cloud head and hitting the surface and propagating forward. And at the time, that was the 5 o'clock in the morning NOAA image, that feature was recognised by the meteorologists on duty. There was already an amber warning out for wind for the central belt of Scotland for the rush hour that day. And the sight of those signatures on the imagery, as well as an observation of a 90-mile-an-hour gust that appeared in Isla, gave confidence that this was going to be an exceptionally damaging event for southern Scotland. So the existing warning was upgraded to red. You can notice those tails which rushed across southern Scotland there. And so yes, so a red warning was issued for the whole of the central belt. And to give a few hours warning that the situation was going to be worse than expected still, warning of gusts of 90 miles an hour. And in fact, the central belt, including the Edinburgh area, had gusts up to 85 miles an hour. And one of my colleagues who lived in Glasgow said the whole system sounded like a roar of an express train going through, and the whole block of flats shook. So it was a really vigorous system. So that's an example of how we can use, one example of how we can use satellite imagery to help refine forecasts. Oh, there's a rather nice satellite image. This was one of only 2 fully fledged tropical hurricanes to hit the British Isles. This was Hurricane Ophelia that hit Southern Ireland in mid-October 2017. You can see the beautifully kind of spiral arms around it, and even the last vestiges of the eye, which helped us to exactly pinpoint where the centre was at the time. And that gave winds of 100 miles an hour at Cork, and absolutely tore the sports stadium to pieces there. And incidentally, the air that came up from the Sahara on the forward side of this gave some beautiful lighting, unusual lighting effects that morning in the Exeter area, and our switchboard was absolutely jammed with people bringing up, not about the hurricane, but what was this peculiar lighting effect? Why is the sky orange? Was it supernatural? One of the key roles of the forecaster is to identify whether or not the model has a correct representation of the state of the atmosphere, because errors in a model's analysis, as you're aware, can magnify into errors in the forecast, often in as little as a few hours. So we very often use satellite imagery to try and identify these such errors. Here's a meteosat image of the Atlantic, 6th of February this year. Now, one ingenious technique is to use the model's own forecast of cloud and moisture to, if you like, reproduce what the model thinks a satellite picture should look at, so-called simulated imagery. And this is an example here of the model's simulated image. Sorry, here it is. The real image, simulated image. So that's actually a pretty faithful representation of the infrared image. So the model obviously knows what's going on. It's a very faithful representation of that cloud mass over Newfoundland. A very faithful representation of the stuff to the north of the UK. But this system to the southwest of Ireland is a developing low. And we notice that you can see there's a sort of a displacement northwards. In reality, the system is further north than the model has got, and it's a bit more contorted. So that is indicative of a possible error in the model. And we can dig down more deeply into that sort of thing. That is from our Met Office global model. So what we can do is we can overlay things like pressure fields from the model onto satellite pictures. So this was a satellite infrared picture about 3 hours later. There's Ireland there, and it shows that cloud system there. And superimposed on the map in black are the surface pressure fields from the Met Office model, and in yellow are the pressure fields from the European Centre forecast model at the same time as the picture. Both of these these are the 2 world's best models. Interpretation of the satellite imagery would suggest that the low pressure centre in that system is where that letter X is, and also supported by data from the buoys and the buoys there. And it's clear, it was clear to us that the Met Office model with its closed isobar there had a much better representation of the low pressure centre than the European Centre model with the yellow isobars, which had a much more bland system. And our global model had gone on to forecast that low pressure centre to move across southern England that night. It's quite a vigorous system, whereas the European Centre model in yellow just moved a very indeterminate system across the south of England, which would have had a very different weather impact. So it gave us confidence to follow a global model's more developmental solution, and to put out yellow wind warnings for the southwest of England for that evening. But remember also, I mentioned that that system west of Ireland was probably further north in reality. It allowed us also to allow for the area of very strong winds to extend a bit further north than the model did. So that's another example of how we can, on a day-to-day basis, spot errors in the model and then determine how to overcome them and correct for them. Okay. Another example of where we use satellite imagery very intensively. It's excellent for the real-time monitoring of thunderstorms, which have a very distinctive satellite signature. You can see here from this aerial photograph from a high-altitude aircraft, this is a thunderstorm system, large cumulonimbus clouds rising, hitting an atmospheric lid called a tropopause and spreading out as this massive so-called anvil cloud, which consists of ice crystals, so it's very cold and high up, and also very bright and reflective because it's very thick. And thunderstorms have therefore have this distinctive circular signature on the satellite imagery. So if I cycle through a set of visible pictures about 15 minutes apart, I've labelled those cells there so you can see how, for example, you can see how they all grow quickly. Secondary cells like A1 and C1 there then develop adjacent often to existing thunderstorms, then themselves expand and go through this life cycle, and you can often end up getting a huge mass of things called a mesoscale convective system, which can give frequent lightning and hail. And monitoring of these sort of systems is very important for warnings for aviation and, for example, for power networks. I'm just going to show you, I realise I haven't shown you many movie loops here. And I may not be able to show you it because I can't find where I've put it.
Is it the E?
Is it the E, this one here?
Yeah.
Oh, yes. I'm glad thank you. Yeah. This is just an example of satellite imagery showing thunderstorms developing over the Gulf of Guinea, in fact. It was earlier this week we grabbed this one. It's a combination of infrared and visible imagery. The cold tops of cloud are highlighted in red there. And you can see just how the explosive development of these systems, and also being a satellite movie loop, it shows how the atmosphere is a fluid. Notice at lower levels, these areas of cloud are moving in completely different direction from the thunderstorms, which are propagating with wind higher up in the atmosphere. So it does give you an idea of the fact the atmosphere is a fluid in reality. By contrast, if we just go to the sort of weather situation we had a few weeks ago at the end of February, when it was, very quiet and arguably quite spring-like, fog can then become a problem. And this shows the benefit of combining different satellite channels. Fog Fog, of course, often forms at night, which itself is a bit of a problem because it means you can't actually use satellite imagery easily at night to show it. But this is where different channels come in. So this is using, in particular, the 3.9 micron channel, which has different radiative properties from infrared. This picture shows immense detail in the fog, detail you would never ever get from surface observations. You get fog in the Exe Valley and Exeter area, up the M5, up the Severn Valley, up the valleys in Wales, up through the East Midlands. And if we'd looked at an ordinary infrared picture like this, we wouldn't have seen the fog because fog radiates at exactly the same temperature as a surrounding land or sea surface. So an infrared picture it wouldn't be there. But use a channel 3 combination, 3.9 combination, and you actually end up seeing it in all its glory. And you can also colour enhance it to make it easier to be picked out. So there's an example of fog anyway. Other interesting phenomena you can see on satellite imagery: mountain waves. When the air moves quickly from west to east, say across a mountain range, under some circumstances, if there's a strong inversion present above the mountain height and a jet stream aloft, you can end up getting the air going over the mountains and forming this wave-like pattern. And clouds tend to form at the crest of these waves, giving these really nice lenticular clouds that conspiracy theorists will look at in darkness in night and say, oh, those are flying saucers because of the shape of them. Much more mundane, they're atmospheric waves. And you can see on this satellite image this rippled effect like sea coming over sand. There's beautiful wave-like effects. And as well as they look very nice, but they're indicative of the fact you'll be getting very strong gusts of wind where the wind comes down rapidly from the mountains and bounces. And you will often find at the A1 you get lorries being overturned through gusts of wind, and aircraft can become difficult to handle. And there's another example of the same thing, with lee waves being set off by Dartmoor and propagating right down into central southern England and coming downwind of Wales. And volcanic ash, another thing that can be picked up from satellite imagery. We incorporate the 12 micron infrared because it has different properties from ice cloud, or the ash has different properties. And in this example from Mount Etna, we can see picked out by the satellite the volcanic plume, and we can use this to verify our atmospheric dispersion models. And of course it's very relevant because ash and jet engines don't go together. It's absolutely catastrophic if ash gets into a jet engine. I remember why they had to stop all the flights in 2010. So, another nice thing, ship trails. On this very high resolution visible picture, those lines are actually trails into low cloud caused by smokestacks of ships. If it's very stagnant, you find the trails just won't disperse, and it gives an idea of the impact that aerosols can have on the formation of cloud. That is a very high resolution satellite picture, probably about 100 metre resolution from an orbiting satellite. So, one thing I haven't talked about, but I think is absolutely essential to mention, is that there's a whole wealth of satellite products that are spawned automatically by satellite and assimilated directly into numerical models without untouched by human hand. Vertical soundings of temperature, cloud track winds, in other words, AI techniques to identify cloud elements, look at that movement and derive winds. Microwave imagery can be used to determine wind strength and direction over oceans where there's virtually no other data, and also in the presence of cloud. So, and vertical soundings of temperature are the data observational source that has the biggest positive impact on weather forecast models, more so surprisingly than surface observations or weather balloons. It's vertical soundings of temperature. So from that perspective, satellite technology has an improved computer modelling. It's had an absolutely profound effect on weather forecasting. And so I hope I've given you a flavour of how we use the satellite imagery in weather forecasting. I've only scratched the surface, but it helps us to add models, add value, and add detail to computer model output, and particularly look for small-scale details. Plus, importantly, it helps us to understand atmospheric processes in much more detail and give us an appreciation that the atmosphere is very much a fluid. So I'll finish there, and I'm sorry I've gone on a little bit long, but is there time for any questions?
Yeah, so thank you, Martin.